On the 14th of July, 1941, a German army logistics officer standing at a busy rail junction in western Russia was writing a routine entry in his daily operational log. The platform around him was full of the organized noise of a successful advance, engines idling, officers shouting movement orders, soldiers unloading crates from flat cars with the efficient confidence of men who believed they were winning. The invasion was 3 weeks old and proceeding on schedule. Nobody at that junction, in that moment, had any reason to expect what was about to happen to them. At 3:15 in the afternoon, a sound arrived that none of them had ever heard before. Not an explosion, not the crack of artillery, something else entirely. A rising mechanical shriek that grew from nothing to overwhelming in the space of 2 or 3 seconds. A noise that several survivors would later describe independently as being unlike anything in their prior experience of war. And then, before anyone had time to react to the sound, the entire station disappeared into fire. Not fire in the sense of burning, fire in the sense of transformation. The junction, the trains, the fuel tankers, the equipment, the men, all of it was simultaneously inside an event that had no precedent in their understanding of what weapons could do. Vehicles that weighed tens of tons were thrown sideways. Fuel stores that had been stable a moment before were now a single connected mass of burning liquid spreading across everything. The ground itself appeared to be on fire, and the soldiers who survived the first seconds and tried to run found that there was no direction in which the fire was not also going. That evening, the chief of the German army's general staff wrote in his personal diary that Russian forces near that junction had employed an entirely unknown type of weapon. He described a storm of incendiary projectiles that had completely destroyed the rail facilities, along with the equipment and personnel of the formations that had been unloading there. He used the word unknown twice in the same paragraph, which for a man of his professional precision was as close to bewilderment as the prose would allow. The German military intelligence apparatus received an urgent directive within hours. Find out what this weapon is, how it works, and where it is being produced. That directive would remain active, largely unfulfilled, for the next 4 years. The secret that the Germans spent the entire war trying to uncover was not where the Soviets had hidden the technology. It was how ordinary food processing machinery had made it possible to produce a revolutionary weapon in industrial quantities. And that answer was so unexpected that German engineers, even after physically examining captured examples, refused to believe it was correct. But the story of how that weapon came to be at that rail junction on that afternoon is itself remarkable, because 6 weeks earlier, the entire program had come within a single demonstration of cancellation. In the 3rd week of June 1941, a weapons review was held at a proving ground outside Moscow. The occasion was a formal inspection for senior military leadership, the kind of event where careers were made and broken, where promising programs received funding and disappointing ones were quietly terminated. The delegation included the most senior uniformed officers in the Soviet military establishment, men who had spent their careers around artillery and tanks and understood the physical language of military hardware on site. The reactive artillery installation was scheduled last. When the senior officers finally made their way to it, the first reaction was visible skepticism. What they saw did not look like a weapon. It looked like a truck with metal scaffolding in the back. Long guide rails bolted to a rotating frame with finned projectiles resting on them like items awaiting delivery. There were no gun barrels. There was no recoil mechanism. There was nothing that corresponded to their mental image of artillery. Several members of the delegation lost interest before the demonstration began. Then the order to fire was given. What happened in the following seconds changed every calculation in the room. The installation discharged its entire load of rockets in a single sustained salvo, and the target area at the far end of the range ceased to resemble target area. The scale and simultaneity of the destruction, not one explosion after another, but an entire zone of ground simply erupting at once, produced a silence among the observers that was, by multiple accounts, the most persuasive argument the weapons advocates had ever made. No words were necessary. The device had spoken for itself. The procurement decision was reached the same day. The paperwork authorizing series production was signed on the 21st of June, 1941, the last day of peace, hours before the German invasion began. The timing was, depending on how one chose to view it, either extraordinary coincidence or the narrowest possible margin by which a decisive weapon entered a war in time to matter. The formal military designation was bureaucratic and forgettable, a production code derived from the caliber of the rocket it fired. The soldiers who operated it, and the soldiers on the receiving end of it, arrived independently at more memorable names. German forces, examining the launcher's guide rails from a distance, compared them to the pipes of a large church organ and adopted that as their term for it. Soviet soldiers, with the preference for the affectionate that has always characterized the Russian relationship with the tools of their trade, named it after a girl. The name came partly from a factory designation letter, partly from a popular pre-war song about a young woman waiting on a riverbank for her soldier to return. The name stuck because it fit. The weapon was loud and devastating, and it came from far away, and somehow the diminutive female name made all of that more bearable. The Katyusha, as it would be known to history, was built in the initial period on a domestic three-axle truck chassis, a vehicle that was available, relatively robust, and capable of moving across the kind of terrain that characterized the Western Soviet Union in summer. Each launcher carried 16 rockets on 8 parallel guide rails. A complete salvo of all 16 required between 7 and 10 seconds to fire, after which the vehicle could move immediately. This was the central tactical innovation that conventional artillery could not replicate, the ability to deliver an enormous volume of fire almost instantaneously and then be somewhere else before a response could be organized. A conventional artillery battery firing the equivalent weight of ordnance needed several minutes, time during which it was stationary, identifiable by the smoke and sound of its fire, and vulnerable to counter-battery response. The rocket launcher was present for seconds, then absent. By the time a German observer reported the location of the fire, plotted the coordinates, and passed a fire mission to their own artillery, there was nothing at those coordinates to shoot at. The first operational unit equipped with the new system was a special battery of 7 launchers under a young captain. The unit deployed to the Western Front in the first days of July 1941, carrying with it strict security orders of a kind that had no precedent even in the Soviet military's extensive experience with operational secrecy. Every vehicle carried a substantial demolition charge. Every crew member had signed a personal oath accepting responsibility for the destruction of their launcher if capture appeared imminent. The paperwork consequences for the loss of a launcher through negligence were severe enough that a commander whose vehicle was captured faced criminal proceedings regardless of the circumstances. When a young soldier managed to recover a disabled launcher that had been left in territory briefly overrun by advancing German forces, his commanding officer reportedly embraced him in front of the assembled unit and wept, because the officer understood that the recovery had saved not just a machine, but his own freedom. The strike on the rail junction was the battery's first combat employment. The second came the same afternoon, when the same launchers were repositioned and fired against a pontoon crossing over a nearby river where German forces had been accumulating, waiting for their turn to cross. The crossing was destroyed. The forces waiting at it were destroyed. In a single afternoon, a weapon that had been a bureaucratic project 6 weeks earlier had twice produced results that conventional artillery would have required hours to achieve and might not have achieved at all. What the Germans found when they eventually captured an intact example and shipped it back to their technical analysis facilities was simultaneously revealing and frustrating. The launcher itself was not complicated. The rocket projectile was not fundamentally different from known principles. The explosive warhead functioned on standard chemistry. The guidance system, such as it was, the rockets being unguided, was straightforward. None of the individual components explained the system's performance in a way that suggested technological secrets impossible to replicate. Except one. Inside the rocket motor, German engineers found the propellant charge, 7 cylindrical sticks of a specific type of smokeless powder arranged in a precise geometric pattern, 6 around the circumference and 1 in the center. The propellant itself, a formulation known as ballistite, was not unknown. It had been used in large-caliber naval artillery for decades, but ballistite propellant sticks of this size, each one 40 millimeters in diameter and more than half a meter long, presented a manufacturing question that the German analysts could not answer. The accepted method for forming large ballistite charges was a hydraulic press. The process was elaborate, slow, and required enormous equipment. You loaded the press with a prepared sheet of plasticized propellant material, applied heat and pressure through a large hydraulic ram, slowly forced the material through a die that gave it the desired shape, then slowly retracted the ram, carefully cleaned the interior surfaces contaminated with residual explosive material, and repeated the cycle. The intermittent nature of the process, the size of the machinery required, and the care demanded by working with explosive materials at elevated temperatures all combined to make production rates low and facilities large. For the specific dimensions of the charges found in the captured rockets, German engineers calculated that the required press would be extraordinary in scale, a machine of the type that, to their knowledge, existed in only one place in the world, at a British facility where it occupied the equivalent of a 4-story building and was operated with exceptional caution because the consequences of a malfunction during operation were catastrophic. They called this type of machine, informally, a mammoth press. German military intelligence received an immediate tasking: identify locations within the Soviet industrial interior where buildings of sufficient height to house such equipment existed, photograph them from the air, prioritize them as bombing targets, destroy Soviet capacity to produce propellant charges, and the Katyusha program would collapse from ammunition shortage regardless of how many launchers the Soviets managed to build. The search ran for 2 years. It found nothing. The reason it found nothing was that the Soviet Union had never built a mammoth press. The buildings German intelligence was looking for did not exist because the manufacturing method that required them had been abandoned in favor of something so different in concept that the German engineers, confronted later with evidence of it, initially dismissed the reports as misinformation. A team of Soviet chemists and engineers working under wartime urgency at the beginning of the war had adapted a Pasteur extrusion machine. This is not a metaphor or a simplification. The device that enabled mass production of rocket propellant charges for the most consequential artillery weapon of the Second World War was derived from the industrial equipment used to manufacture spaghetti and macaroni at food processing facilities in peacetime. The screw-feed extrusion principle, forcing a viscous material through a shaped die to produce a continuous strand of consistent cross-section, worked for propellant as it worked for pasta, provided the machinery was sufficiently reinforced to handle the much greater resistance of the material, provided the die and feed mechanism were heated to maintain the ballistite at the precise temperature required for forming, and provided the operation was managed with the continuous attention and strict discipline that the process demanded. The crucial differences from conventional press forming were operational rather than conceptual. The extrusion process ran continuously rather than in cycles. The material moved through the machine without stopping, emerging as a strand of the correct diameter with the correct central channel, needing only to be cut to length and cooled. Where a hydraulic press produced one batch at a time and required the entire sequence of loading, pressing, retracting, and cleaning between each batch, the extrusion machine ran like a production line, its output limited mainly by how fast material could be fed in at one end and cut to specification at the other. The productivity difference was not incremental. By the estimates of those involved in developing the process, the continuous extrusion method produced somewhere between 8 and 10 times the output of the hydraulic press approach per unit of floor space and time. Facilities housing this equipment needed no special structural height. They were ordinary single-story industrial buildings with the standard earthwork blast containment berms that any explosive adjacent production facility required. From the air, they were indistinguishable from warehouses. The limitation of the extrusion process was operational discipline. The machine could not be stopped for more than a few minutes without consequence. At the temperatures required to keep the ballistite material workable, an extended halt allowed thermal decomposition to begin in the material inside the machine. A process that, if allowed to continue, would produce an uncontrolled energetic event that would destroy the equipment and everything near it. Brief stops produced defective product. Extended stops produced disasters. Every operator in every facility understood that keeping the machine running was not a matter of production efficiency, but of survival. The workers who ran these machines throughout the war were predominantly young women. Some of them were barely past the age of school completion. They worked shifts that extended well beyond what peacetime labor law would have permitted, in conditions that combined the tedium of repetitive industrial work with the specific anxiety of handling explosive materials, and they did this continuously from 1941 through 1945 because there was no alternative and because they understood what the product was for. Accounts from veterans describe factory floors where the workers addressed the launchers being loaded with finished rockets before their departure for the front, speaking to the machines directly, urging them to do their work and promising to keep the supply coming. It is not a sentiment that translates easily across contexts, but the emotional reality behind it is not difficult to understand. The system very nearly collapsed anyway, from a direction that had nothing to do with German military action. Ballistite propellant, like many energetic materials, requires chemical stabilizers to remain safe during storage. Without stabilizers, the propellant undergoes gradual self-decomposition, a slow chemical process that initially reduces performance and eventually, if allowed to proceed far enough, produces propellant that can detonate spontaneously. The specific stabilizer compound required for the Soviet formulation was a petroleum derivative that the Soviet chemical industry did not produce domestically. It had been purchased from Romania. When Romania entered the war on the German side in the summer of 1941, the supply stopped. The stockpiles that had accumulated were finite. Shipments arranged through British suppliers were intercepted and sunk in the Atlantic approaches. Propellant production began to decline as stabilizer reserves ran down, and the operational tempo of rocket artillery at the front slowed noticeably. German intelligence noted the reduction in Katyusha activity and concluded, reasonably but incorrectly, that the program was reaching the end of its productive capacity. The same team of chemists who had developed the extrusion manufacturing process was directed to find a domestic substitute for the imported stabilizer. The search was conducted under the specific kind of pressure that characterized Soviet wartime science: continuous work, round-the-clock availability, and the understanding that failure was not an outcome that would be accepted. They found a solution. A domestically available compound achieved the necessary chemical stabilization at acceptable production cost. The formulation was adjusted. Production resumed at full rate. The team responsible received a state prize for their work, and the German assessment that the Katyusha problem had resolved itself was proven wrong in the most emphatic way possible. As the war continued and Soviet manufacturing capacity expanded and relocated eastward beyond the reach of German air power, the launcher itself underwent continuous development. The most significant change in the primary version was a new chassis. The original domestic truck had been adequate but limited. Production had been disrupted by the industrial evacuation of 1941, and replacement vehicles were not consistently available in the quantities that the expanding rocket artillery program required. American trucks supplied through the Wartime Material Assistance Program solved this problem. The six-wheel drive American vehicles that began arriving in quantity from 1942 onward were, in the assessment of the Soviet engineers who worked with them, superior to any domestic truck then available as a launcher platform. The all-wheel drive system gave them cross-country mobility that allowed launcher units to move across terrain that had stopped wheeled vehicles before. The approach clearance was sufficient for water obstacles that would have damaged lower-slung domestic vehicles. The load capacity, officially specified at the conservative American rating, was routinely exceeded by Soviet operators who quickly determined how much more the chassis would actually carry. The combination of a productive launcher and a capable carrier produced a system that could keep up with the mechanized formations it was supporting across almost any terrain the Eastern Front presented. The BM-13 was the center of the family, but not the whole of it. A smaller caliber system fired rockets derived from aircraft armament, producing a weapon light enough to be mounted on platforms that could not carry the heavier launcher. Light tanks, river patrol craft, railroad flat cars, and in mountain terrain where neither tracked nor wheeled vehicles could maneuver effectively, simple ground frames that allowed firing from fixed positions. These smaller systems extended the reach of rocket artillery to environments and unit types that the main launcher could not serve. At the other end of the spectrum, a heavy variant carried warheads that dwarfed anything in the Standard family, nearly 6 times the explosive content of the regular rocket, in a projectile whose proportions were so unusual that soldiers gave it an affectionate nickname based on its appearance. The heavy rocket's range was substantially shorter than the standard version, a consequence of the aerodynamic penalties imposed by the large warhead. But within its range, the destructive effect was of a different order entirely. Where the standard weapon destroyed in area, the heavy weapon destroyed in depth, collapsing reinforced structures, penetrating multiple floors of masonry construction, producing craters that fundamentally altered terrain. In urban combat, where defended buildings required not just suppression but physical destruction, the heavy variant was the instrument of choice. By the middle of the war, what had begun as a single battery of 7 vehicles had become an independent branch of the Soviet military with its own command structure, reporting directly to the Supreme Command rather than through the conventional artillery chain. The designation given to these units, Guards Mortar, carried the Guards prefix that was the Soviet military's highest form of institutional recognition, and it had been awarded before these formations had fired a single combat round, purely on the basis of the weapon they carried. No other unit in the history of the Soviet armed forces had received that designation prior to proving itself in battle. The decision to do so reflected an assessment at the highest level of the military leadership about what this weapon represented and what role it would play in the war to come. The scale of production that followed justified that assessment. Thousands of launchers were built, dozens of varieties of rocket were developed, tested and fielded, different calibers, different warhead configurations, different ranges, different fusing options for different target types. An entire ministry was created whose sole responsibility was the production and supply of rocket artillery material, an institutional dedication to a single weapon type that had no parallel elsewhere in the Soviet defense structure. The production facilities expanded continuously, new plants were constructed in the eastern industrial regions, and the monthly output of rockets grew from the hundreds in 1941 to the tens of thousands in 1944. The operational record of the weapon across those years covered every major engagement of the Eastern Front. At Stalingrad, massed rocket salvos fell on the encircled German formations through the winter of 1942 and 1943, contributing to the sustained attrition that made the eventual German capitulation inevitable. At the Great Armored Battle of 1943 in the Central Soviet Union, rocket artillery met the German armored offensive with fires that stripped the accompanying infantry from the tanks and left the armored formations fighting without the infantry support on which tank tactics depend. In the operations of 1944 that rolled German forces back across the length of the front, rocket artillery was the instrument of the preparatory fires that preceded each offensive, softening the defensive positions that the infantry would then assault. In urban fighting, the heavy rockets proved their particular value. A defended building in a city environment is a difficult tactical problem for conventional artillery. Hitting it repeatedly with standard shells produces damage to the structure, but may not kill the defenders sheltered in its lower floors and basement. A heavy rocket striking the same building delivered 30 kilograms of explosive in a single package, and the combined effect of the blast and the structural collapse it produced was categorically different from the cumulative effect of multiple lighter rounds. Strong points that would have required sustained artillery engagement over hours were reduced in single salvos. The tempo of urban operations was directly affected by the availability of heavy rocket support. Because the constraint on how fast attacking infantry could move through a defended city was often how quickly the fortified buildings blocking their path could be made untenable. The final offensive of the European war concentrated rocket artillery on a scale that made everything that had preceded it seem modest. In the assault on the German capital in April 1945, over 1,500 launcher vehicles and nearly 2,000 additional ground-mounted firing frames were available for the operation. When the preparatory fires began in the pre-dawn darkness, the volume of rockets in the air simultaneously was sufficient to be observed as continuous light on the horizon from distances of many kilometers. German defenders in the western suburbs described the experience of being under this fire as unlike anything in their operational history. Not because the individual weapon was novel to them, they had been fighting against it for nearly 4 years, but because the scale at which it was now being employed had no precedent. In the city itself, during the final days, rocket launchers fired at ranges measured in hundreds of meters rather than kilometers, direct support of individual assault groups attacking specific buildings, the weapon being used at ranges so short that the rockets barely had time to stabilize in flight before reaching their targets. The same system that had been designed to deliver fire from concealed positions at standoff range was, in the war's final act, fighting in the streets. The German engineers who spent 4 years trying to understand how Soviet industry was producing rocket propellant charges in quantities that should have been impossible given what those engineers understood about manufacturing technology, never arrived at the correct answer. The evidence was, in retrospect, available to them. Captured facilities, interrogated workers, examined equipment. The clues were all present in some form, but the answer was so far outside the frame of reference of engineers trained to think in terms of purpose-built industrial machinery that it remained invisible. They were looking for a 4-story press building because they knew that only a 4-story press could do what the evidence showed was being done. The possibility that a food processing machine could do it instead simply did not occur to them as a hypothesis worth testing. This is the final observation that the Katyusha's history invites. The weapon itself, the principle of massed unguided rockets fired in rapid salvo from a mobile platform, was not, in concept, beyond what other military establishments could have developed. The Germans had their own rocket artillery. The Americans developed rocket systems. The British had programs. None of them achieved what the Soviet system achieved in terms of production scale, operational deployment, or battlefield effect. The difference was not technological in the narrow sense. It was the willingness to find solutions in unexpected places, to look at a pasta machine and see a propellant press, to recognize that the correct answer to an industrial problem might not resemble any industrial answer that had previously existed. The engineers who developed the extrusion process were not working from a position of strength. They were working under extreme time pressure, with limited resources, in the knowledge that failure had consequences they would personally experience. The solution they found was not elegant in the way that precision engineering is elegant. It was practical in the way that survival is practical. The weapon that was named after a girl, that was built in secret and guarded with lethal seriousness, that was almost cancelled on the afternoon before the war that needed it began, that survived a supply crisis through an invention that German intelligence literally could not find because they were looking in the wrong kind of building. That weapon traveled from the western borderlands to the center of Berlin in 4 years, and the trail it left is still visible in the design of every multiple rocket launcher built anywhere in the world since 1945. Everything that came after learned something from it. Nothing that came before had done what it did. The Katyusha was not the most sophisticated weapon of its war. It was, in the judgment of the war itself, one of the most consequential.